Well, so what we need to do then is we need to date the age at which these things grow. So this then is the depth into one of these manganese nodules. It's a bit like sort of onion skin, so you can just sample different depths. You can then measure the 230 thorium to 232 thorium ratio, and the value at the surface, you can think of as the initial value, and then as we go deeper into the older layers, that 230 thorium decays away. And you can see as we go deeper in the nodule, the 230 thorium to 232 thorium ratio declines, and then we can just simply solve this and obtain the growth rate. Again, we'll do this in the practical. Okay, so that's one example where we can use the sort of the difference in geochemical behaviours. We can look at even shorter time scale processes. So if we go down through the 238 uranium decay scheme even further, then we go down all the way here, and let's say we get to radon. So radon's a gas, wants to be in the atmosphere. Now, if we have our mineral buried deep in the earth, well, that radon's under pressure, it's not really going to go anywhere. But let's say we've got granite on the surface, and it's exposed to the atmosphere, or we've got fluid flowing through a rock. Then that radon, when it's formed, can escape into the atmosphere. Okay, it's only got a half-life of 3.8 days, but that's long enough, it can get into the atmosphere. Once it's in the atmosphere, it goes through some really short-lived isotopes. Polonium-218, 3 minutes, astatine-218, second and a bit, and radon-218, well, milliseconds, 214 polonium, microseconds. And it gets to lead-210. Lead-210 has got a half-life of 22 years or so. Now, lead is not a gas. The elemental lead in the atmosphere, then it's going to fall out from the atmosphere pretty quickly. Lead is also pretty insoluble. So if it falls into particularly shallow water, it's going to be very quickly precipitated out and accumulated in sediment. So if it accumulates in the sediment, then again it has separated from its parent isotope and it's unsupported. So that 210 lead is then sitting in our sediment, it's going to decay to 210 bismuth. It's a little bit more complicated than that because sediments do contain uranium and thorium. So actually, not all that lead-210 is unsupported, but there will be additional lead-210 which comes from this decay of radium-222.
So the A notation is just a single year or a year?
Yeah, so A just stands for year, beg your pardon. So it's actually what we measure is the excess lead-210. And that excess lead-210 is going to be equal to the initial lead-210 times e to the minus lambda t. So now we're looking at an isotope which has a half-life of only just over 20 years. As a rough rule of thumb, an isotope is useful for dating processes which last about 5 times its half-life. More than about 5 times its half-life, then pretty much it's decayed away and there's not enough for us to measure. But up to 5 times its half-life can work pretty well. So this is a profile of excess lead-210 in some sediments from the salt marsh. Now, the units are becquerels per kilogram. Now, we actually, lead-210, we're not producing a lot of it, and it decays relatively quickly. So the actual concentration in, if you like, sort of ppm or whatever like that, are extremely low. And it's very hard to actually measure it from sort of, classical ways of measuring the concentration of an element. The most sensitive way of measuring lead-210 concentrations is to measure the radioactive decay signal, which is associated with its transformation to bismuth. So it's a beta decay, it kicks out an electron, and that electron has a very characteristic energy. So each beta decay, the energies are slightly different. So if you've got a sophisticated radioactive counter, you can actually measure which energies or which sort of energy each decay is associated with, and that can tell you which isotope is decaying. So you can then measure the activity of the lead-210, it's radioactive decay. And what the units for that are becquerels, that's the unit of radiation. And what we see in this salt marsh is at the surface, then the activity of lead-210 is a shade under 100 becquerels per kilogram. By the time we get down to 10 centimetres, that activity has dropped down to about 35 becquerels. So the half-life is 22.3 years, so lambda decay constant 0.03 years to -1. So we can determine then this ratio at a particular depth, and that tells us that the age of these sediments at 10 centimetres, and we go through in exactly the same way we did for potassium argon, the age at 10 centimetres is 33 years, and that depth is 10 centimetres, therefore the sedimentation rate is 0.3 centimetres per year. So we can use the uranium series decay scheme that various sort of intervening isotopes, when they drop out from that decay scheme, to look at a wide range of processes going over a wide range of timescales. Okay, so what you need to be aware of is then how these uranium thorium series isotopes differ from the rubidium, strontium, samarium, indium isotopes. Because there's not just parent going to daughter. There's a lot of intervening steps, and that can create some differences. You need to know how in zircon, how the lead isotopes can be used to derive these two ages and what those ages mean. And this is, for geologists amongst you particularly, this is really important. And then you also need to understand this concept and what we mean by unsupported isotopes. Again, this is, for oceanographers amongst you, this is really important because there aren't many isotope decay schemes that can be used in marine geochemistry. And uranium series is one of the best. Okay, so let's see how much attention you've been paying here. Okay, so helium-3 and helium-4, two isotopes of helium, both present incorporated into the Earth when it finished first formed 4.5 billion years ago. Okay, neither of them are radioactive. They can escape from the atmosphere, but they escape from the atmosphere in the same rate. So, this helium-3, helium-4 ratio of the Earth higher or lower today than when the Earth first formed? No, not the same? Higher, lower, you're 50-50? It's lower, because we've been kicking out all this helium-4 from the uranium series. So it's lower than today. So bearing that in mind, which types of rocks should have the lowest helium-3, helium-4 ratio? Well, the ones we've got lots of uranium. The ones that have got lots of uranium in are in the continental crust. Because when you have partial melting in the mantle, uranium likes to go into the continental crust. So as a consequence of uranium series decay, thorium series decay, we also have different reservoirs on the Earth, have different helium isotope compositions. And that's actually can be quite useful in looking at various processes that are going on here. Okay, so which stable lead isotope is produced from decay of uranium-238?
206.
206.
207.
207.
208.
208. Okay, multiple of 4. Remember that. Okay, so these are all these helium isotopes that are being kicked out. So a lot of